Um, Sometimes I put things in quizzes that I forget that I put on quizzes, and then I don't cover them in class. That was one of these things. So I showed you how to do relative frequency diagram or tables. It's basically just like percentages, more or less, but in proportion form. A cumulative frequency distribution, what it does is cumulative measures everything at or below a certain observation. So like here, the 0 to 3.9, that covers like 21% of the population. And then as you go up, so then you could start accumulating the proportions, and then it's telling you everybody that's at or below that new threshold. So like if you bump up to 7.9, well, 47% are in that range, but 21% are also below that range. So at or below, so if you go up to 7.9, there would be a 68%. So you basically combine them below that threshold, and that's how a cumulative distribution works. It's just that you take the relative frequency, and then these numbers increase up to 1 based on how much probability or how much percentage you're gaining as you go from one category to the next. That's what a cumulative frequency distribution is. Yeah.
So is the bottom right one always going to be 1?
It should, yeah. And if it's not 1, you have a problem. It's basically like yesterday. I wanted to make sure our samples, they added up to 40 or 50 or whatever the total was. Your relative frequency should always add up to 100%. That's true. Or something really, really close to 100%. There could be like rounding errors sometimes, but it should be like 0.999 or 1.001 or something, or 1 exactly. Something in that range. Yes. Good question. Was there anything else that you came across that you wanted to ask about the quiz? I think that was, yeah.
Maybe another way, I don't know if that would be helpful, but maybe another way to find the answer at the point 2.21 plus
Yeah.
the 0.47.
Yes.
And whenever we get that,
Yeah.
that 0.16.
Exactly. Yeah, and then you just add the next one, and then you just add the next one. You just add the next one. Yep. Mm-hmm. That's the idea. All right. Hey, that was a really good question you asked. I think I just gave you the answer to it. All right. Any other questions before we scooch along? Okay. And there's some quizzes coming up due as well. So I think there's one. Is there one tomorrow?
One today and one tomorrow.
Yeah, and the one tomorrow, it's not going to be that bad. It's like all that graphing stuff that we went through yesterday. I don't think. But anyways. There's just a lot more quizzes at the beginning of the course than there are later in the course. They start to get spread out as we start to get less concepts and get more detailed. But it's just at the beginning we cover so much stuff, just kind of just get it all out of the way. So I break it into smaller quizzes. So, all right, let's get moving. We ended in Module 2, but I was just finishing going over the importance of graphs. So Module 2, Part 1 was just all about the graphical summaries. So today what I want to look at is we'll go through now, start to look at some of the numerical summaries. And this is where we'll start to do some more calculations, and it'll feel a little bit more like a math class. So whenever my computer decides it's ready to work with me. I forgot to bring these up earlier. Come on now. You can do it. You can PowerPoint. Come on. Maybe I get Canvas so it's not thinking. Yes, I know. Aha. Thank you. Well, let's make it wider, might as well. Let's get started. Sorry. Okay, so yesterday we talked about the graphical summaries, basically, so tables, pie charts, bar charts, histograms, just ways that we can kind of visualize data to get an idea of like maybe the shape or if there's any weird stuff happening in the data set. So once you have that, then we move on to calculating numerical summaries out of our data set. And so yesterday, I was telling you there was 3 characteristics of data distributions, right? So we're normally interested in their center, their spread, and their shape. And I told you yesterday, this we pretty much get from graphs, but the center and the spread, that's where we really like to get a little more detail or a little more specific, and so numbers can do that because different types of numbers tell you different information about a data set. All right, so that's what we're going to work on today. So measures of central tendency, also known as measures of center. So these are numbers that attempt to measure the center of a data set. So, and you probably know some of these. I think we listed some yesterday. What are some measures of center of a data set? What do you think? The median is a good one. The what? Yeah, the mean or the average. And then there's usually another one that goes along with that some people use, although it's not really a great measure of center, honestly. Sometimes you'll hear the mode. Yeah, the mode. Okay, so the mode, this is just the most common. This is not a commonly, wait, I should finish. Most common observation. That's what the mode is. That doesn't even look like a word, but it's supposed to say observation. The mode just means the one that pops up the most often, but it's not a statistic that we use a lot. And it's because it doesn't have, it could be anywhere in your data set, at the low end, the high end, the middle, and it's not something you compute mathematically like an average. And so it's just hard to work with, so the mode's not used very commonly. But some applications might be interested in. So we're going to actually we're going to focus mostly on medians and means, and then some of the differences between them and how different shapes could affect them. So the mean is the average, right? So how do you calculate the average? Yeah, so the mean, you just sum up. It's the sum of all the observations, and then what do? Yeah, you divide by the number of observations, or in the case of how we've used it, we call that sample size, right? You divide by however many samples you have. So there's some notation we're going to start to introduce here. This is notation that's like common across all statistics. Anytime you're talking about a mean, if it comes from a sample, there's this little symbol we use, which is it's called X bar, or a bar, it's just an X with a bar on top of it. It's called X bar, but what it means is it always refers to a sample mean. Okay. So anytime you ever read a textbook, involving statistics, or a research paper involving statistics, if they write X bar, they always mean sample mean. Always. That's like one of those symbols that's just set aside in statistics, and it never means anything else. There's not a lot of those, but there's some of them in statistics, and that's one of them. Okay? Now, there's also another pretty much commonly accepted notation. So typically, if we're talking about a sample size, then we use a little n to denote sample size, always. So again, if you're ever reading a research paper or anything like that, they will always, always, always write little n to mean sample size. That's standard. Okay? So far, so good? Okay. Now, this, writing sum of all observations, in math, we just don't like to write. We'd like to try not write as many words as we can, and so rather than spending a lot of time, writing out a phrase, we'll try to shorthand it. So the sum is something that pops up a lot, and so there's something called summation notation, and this is not really like the main focus of the class, but you need to kind of understand it because we have it in some of our formulas. So let's say, here's what your data set looks like. Okay. So you have in your data set, basically you'd have a bunch of individuals, and maybe they're numbered all the way up to like person n, right? Because we always use little n for sample size. And then for each of those individuals, you're going to go and you're going to like observe something about them, right? Some variable. So we'll call it variable x. Like maybe you're observing how many hours of sleep they got last night. You're going to observe that about everyone. Okay, so you're going to go to the first person in your sample, and they're going to give you a number, right? And you don't know what that number is in advance, but so what we'll do is we'll just call it x1. It's going to be some number between probably like 0 and, well, it has to be between 0 and 24 or something, because I don't know who sleeps more than 24 hours, but it's just some number, and they're going to tell you how many hours they slept. And so we use this right here. This is called subscript. Okay? And the subscript, it's like an index that tells you who that's attached to. So that first observation, x1, is going to be the response from person 1. So then person number 2 is going to tell us something, and person number 3, and person number 4, and then everyone's going to give us an answer, you know. And so this right here, this is really like your data. This is like your numbers, right? Okay. Well, so if you're going to take those numbers now, and you're going to turn them into an average, okay, or a mean, right? So like you're going to calculate the sample mean, x bar. That's why we use a little x to denote the sample mean, because we think of like the observations as like numbers, they're x values kind of. Okay, so what are you going to do to calculate the sample mean? You're going to add up all of those x values, and then you're going to divide by what? Little n, yeah. Okay, right? That's what the formula tells you to do. I'm just not using specific numbers yet, but that's what it tells you to do. Add a bunch of junk up, and then divide it by however many things you saw. Okay, so then what we do is, because this right here, this is just the sum of all the x's, right? Yeah. No, you're good.
What is the x represent?
It's a variable. Like going into the study, like because we're trying to use like general notation. So for any general study, you're going to go get a person and they're going to give you an observation. So it's a variable. It's just a placeholder for whatever number that first person is going to tell me. So in the case of nights of sleep, this could be like 7.5 or 8.2, whatever the person tells me. But going into the study, I don't know what they're going to tell me. So I'm just going to give it a variable.
Okay.
Your x1, your x2, your x2. Yeah. Does that make sense? Yeah. And then when I go to average them, basically you'd end up adding them all up and dividing by the sample size. Okay. So because that sum comes up a lot, we have this thing called summation notation. So this chunk right here, all right here. So summation notation. This is where I'm actually going to show you what it is. We use a Greek letter. It's a capital sigma. Okay? And the capital sigma tells you to add a bunch of stuff up. And then next to the sigma, you tell people what to add up. And so what are we adding up? We're adding up all the x's. And sometimes you'll see it with like a subscript, just like all the xi's. And what this is saying is the sum, or the sigma says add up all of, and then over here we tell you what to add all up. And this is the x, we call them the xi's, but really it's like the I is just a placeholder for all of the values. You know, it's the x1 and x2 and x2. The I is just there as a placeholder. But so then the sample mean formula can be simplified. The sample mean is just the sum of all of the x's divided by the sample size. So that would be the formula we would use to show the sample mean calculation. So that way you don't have to describe it in words, or you don't have to write out a big sentence every time. It's telling you what to do. What are you going to do? You're going to add up all the values, and then you're going to divide by
Why'd you do xi to the fifth power? Or is that?
Oh, I don't know. I think that was supposed to be an S, and I don't know why I wrote it way up there. I don't know what I was thinking. The I here is a placeholder. And it's because, actually, you don't need to write all this down, by the way, if you don't want to. You might have already done it, sorry. But it's not like you really need to necessarily understand exactly the definition. But a lot of times the summation itself will tell you like where to start tracking the data and where to end it. So like if you just wanted to add up like the first 4 observations in your data set, you could actually add some information here and say, okay, let I go from 1 to 4. And so like maybe, and then that would just be equal to x1 plus x2 plus x3 plus x4. So you can actually tell the indice like which ones to add up. Or if you wanted to add up, if you wanted to start the 4th one and go to the 10th one, you could say I goes from 4 to 10. You can like change which ones. But if you want to add them all up, we usually don't add that notation. And then the implication is add up everything. So, anywho, that's a long story for a formula, but that's the story. That's called summation notation. And we use it here, and we have one other formula where we're going to use it. Maybe more than that, actually. There's a few formulas that use it in this class. Just think of it as adding. Okay. Now, along with notation, because it's everybody's favorite thing in the world, along with definitions, I'm sure, there's a little more notation we have to get out of the way. So for the mean, we talked about, so at this whole time, remember, we're dealing with the big picture of statistics. And what happens is, you have some population that you wish you could observe and know about, but in reality, you're never actually going to observe that whole population, right? You're just stuck with your sample. All right. Did I start my recording? Does anybody remember? I did?
Yeah.
You guys are awesome. Look at you. All right. You guys should get paid for keeping track of me. So we have notation to separate the two. So the sample mean we call x bar. I already told you about that. And then if you're talking about, sorry, not sample, population mean, we use a different. So population mean, we use a Greek letter called mu. Okay, it's just like a fancy cursive M or like a U with a tail, however you think of it. It's called mu. And so we use it to distinguish between whether or not someone's talking about the population mean, which is probably what they actually want to know, or if they're talking about a sample mean, which is a number that was calculated from sample data. And you want to know the difference when someone's telling you. If someone's telling you that the average was this, you want to know whether it was a population mean or it was a sample mean, because the sample mean means something different. But typically, then in the big picture of statistics, what we're doing is that we are going to be using x bar in order to estimate mu, right? That's kind of that's how it connects to the big picture. Okay, the mu is the number that describes. The mu is an example of a. I should add it over here. The mu is an example of a parameter. We talked about parameter versus statistic, and the x bar is an example of a statistic. Right, because parameters describe the population, and statistics describe the sample. Okay. All good so far? All right, a little bit of notation. So, not that hard to calculate means. I'm pretty confident most of you can do it, but here's an example. Let's say that you were observing pulses of 9 students, and these are what you recorded. Calculate the average pulse rate. So, if, say this is a sample, then we're just going to add up all of those values, right? So go ahead and pull out a calculator, and you can just sum these up. What's the sample size here? 9? 9. Something like that. 74.2. Perfect. And then the units of the mean are just the same as the units of whatever you're measuring, right? Okay. So it's just adding them all up, dividing by however many are, boom, you get your mean. Everybody okay with that?
Yeah.
I'm very confident that you can calculate averages. You've probably done it for a long time. For some reason, it seems like when I was in school, we did mean, median, mode like literally every year. It didn't even matter what class we were in. I don't know why. We always did mean, median, mode. Okay. So then the median, to go along with it, it is not the same as the mean. When you're finding the median, it's a two-step process. What do you got to do to your data first? Yeah, so you got to order your data like least to greatest. I mean, you could go greatest to least, but it's just go least to greatest, like normal people. And then once you order your data from least to greatest, then what do? I've never heard of a rainbow, but I like what you're saying. You're going for the middle.
Yeah.
Yes. You'll just have to show me. But it depends. It depends because if the data set is even or odd, it changes how you pick the median. Because if the data set is odd, it's easier because then you're going to have a value like dead center, right? If there's like 11 observations, there's going to be 5 on the bottom and 5 on the top and 1 right in the middle. So if n is odd, it's easy. You just pick the middle number once you've ordered it. If n is even, though, anybody know what you got to do? You average them. Yeah. You calculate the mean of the middle too, because there's not going to be a middle number in an even data set. It splits evenly. So 12 observations, there's 6 above, 6 below, right? And there is no number in the middle. So you just knock one off. No, you just take those 2 middle ones and average them out. So we'll do an example of both. But more or less, it's the middle number. And it's the point where half of the observations are below and half of them are above. So it really is it's a very decent measure of center because it literally splits your data in half. So, all right. So, could we calculate a median pulse rate? I bet we could. So first, we just got to order it. Okay. So it's going 60, 60. What else is in there? 73 is 72, then 73, and then and then it bumps up to 80 twice, and then 81, 86. Did I get 1, 2, 3, 4, 5, 6? Yeah. So in this case, it's an odd number, right? So there's just going to be 4 below, 4 above, and then in this one, it just has, it's just 76. There really is no notation we use for the median. Oh, and it would be in beats per minute. Yeah.
So only like 1.5 away from the mean.
Yeah, this one's pretty close to the median in this case. The mean and your median are pretty close, which actually means something. When your mean and your median are close, and we're going to talk about that a little bit here soon. Okay. All right. Everybody feel like they could do a median? Don't forget to order the data first. I see that mistake more often than you think. So you can't just if the numbers aren't in order, you can't just pick the middle number. You got to order them first. Anyways, all right. So one thing I want to look at though is in this case our mean and our median were pretty close. What I'd like to know is I kind of want to look at what happens when you introduce other types of numbers. So here, let's say that a 10th person came in, and that was their pulse. Okay, so what about that person is? What do you notice immediately? Maybe, yeah. They have. It's definitely an outlier. Okay, for some reason their pulse is very, very low. Okay, and it's not like crazy low. I'm not gonna send them to the hospital, but it's way lower than most people. So I want to look at what happens if we redo the median, for example. Okay, so if we redo the sample mean, and now we add up all the values plus that person, and then what would our denominator be then? Now we'd have to divide by 10, right? So calculate that for me if you don't mind. 71.7. Anybody else get that? Not that I don't trust you, I just like to get. Okay? Yes, you say it. Yeah. Yeah. So I actually have had that happen where someone just wanted me to move on. So they were like, yeah, that's right. And then later we figured out it was wrong. I was like, oh, dang, I got to stop trusting you guys so much. But what was it before the outlier?
74.
Yeah, it was like 74.2. Okay? Now, if we go and we recalculate the median, though, all it's doing, I'm not even going to rewrite the data, but all we're doing is we're now tacking on a number down here, right? Yeah, so our median is going to get shifted over. So,
74.5.
yeah, I guess I am going to rewrite my data, but yeah, at this point now it's become an even data set. And so if you try to split the middle, it's not going to work because there's 1, 2, 3, 4, 5, and then there's 1, 2, 3, 4, 5. There is no middle number. Sorry, that's a 73. So this is one of those situations where we need to average those two, right? So it'd be so our median would be 73 plus 76 divided by 2. Okay, and what does that come out to be?
74.5.
74.5. Is that right? That one I do know. I can do that one in my head. But what was it?
It was 76.
It was 76 before?
Yeah.
Okay. All right, so which one moved more?
Median.
This one moved. The median moved dropped by 1.5. What about the mean? The mean dropped by 2.5. Right? So what we notice is, the mean dropped more. Okay. That's actually going to always be true with the mean versus the median when you throw in kind of outlying observations. In fact, it could have gotten even crazier. Like, it wouldn't work because these are pulses and people have to be alive. But what if that number right there would have been like 2, right? Like if this number changed to 2, what would happen to that median? It'd stay exactly the same, right? Because that 49 is just hanging out at the bottom of our data set, and no matter what number I would have told you down here, our median's not going to change. I could have told you this number is like negative 7,000, and what's going to be the median? It's still going to be the average of those two numbers. But if this number was negative 7,000, what's it going to do to the average? It's just going to destroy it because it's going to make the average way negative. In fact, so the bigger the outlier, the more it's going to mess with your mean. But the median doesn't care about the magnitude of the outlier. It just respects that it's out there, but not how far away it is. And then whereas the mean's much more sensitive. So we talk about an outlier. Outliers, we're going to come up with some ways to kind of find outliers. But in general, what is an outlier? It's outstanding in what sense?
From the other data set.
Mm-hmm. Yeah, it's very set apart from where the other data more or less lies. So I just define outliers. These are individuals which are not representative of the majority of the population. That's not like an exact definition. Lots of people could define a lot of different ways, but that's the way I think of an outlier. It's someone who's not representative of us, normal people, right? Okay. It's like your Bill Gates or your Jeff Bezos kind of income. If you're talking about money, it's like just not representative of most people. Okay. Now, what happens though is if you find out you have outliers, or you're working with a data set that has outliers, it affects the median and the mean differently. And so when you're talking about different measures of like center or different measures of spread, it's like, okay, well, why would you pick one over the other? And it turns out one of the reasons you might pick one over the other is if you have a data set that has outliers. Because we have what are called resistance statistics. So like the median is resistant to outliers. And what that means when we say resistant, we're just saying not heavily affected by. That's what we're really. So the median is not heavily affected by outliers. It's resistant to outliers. Then, whereas the mean is not resistant. Not resistant. So the mean can be heavily influenced by outliers. So if you have a data set with outliers in it, then the mean is not actually necessarily a very good measure of the center, because it can be artificially inflated or deflated based on outliers. So the mean is nice for a lot of reasons, which we're going to find out in this class, but it's not always the best. So, okay. This comes back to what we were talking about yesterday when we were talking about the shapes of data distributions, because sometimes, let me see how many. There we go. So, like, when you have, if you have a symmetric distribution, say. So, like we were talking about a bell shape, right? Then, in a bell-shaped curve, mine's crooked, but that's okay. What's true? Like when we talked about heights or things that have normal distributions. What did I mention about sort of like the super tall people or the super short people?
Usually the same amount on either side.
Yeah, it's usually balanced, right? So in a symmetric distribution, what happens is that there might be outliers in there, but the outliers are going to kind of be balanced on both sides. You're going to have about as many very short people as you're going to have very tall people. And they're going to be about equidistant from the center. So like someone who's really short might be like 2 feet below average, and someone who's really tall might be 2 feet above average, but it's like the equal distance on both sides. Okay. All right. What happens though is in a skewed distribution, the balance gets messed up. So like if you have a skewed right distribution, in a skewed right distribution, where are all your outliers? Yeah, there's only outliers at the top. Really, nobody at the bottom there is an outlier. So like if we talked about this is like income or like number of children, right? Even people with no children aren't really outliers, because there are really no outliers on the bottom end, because they're down here with most of the population, and there's lots of people with no children. Okay, and so there really are no outliers at the bottom. But then you have the opposite effect in a skewed left distribution. In a skewed left distribution, where are all your outliers? Yeah, all your outliers are at the bottom.
What was an example of that one?
What did we use for examples of that one, actually? Now I'm trying to remember. I know, like,
GPA.
yeah, like age at retirement, right? I mean, even someone who retires pretty old, maybe in their 70s or 80s, they're not really outliers, because most of the rest of us are also somewhere up near them. The only real people we consider outliers are people who retire very young. Yeah, exactly. Yeah. So what happens, though, is because the outliers get out of balance in a skew distribution, then that has a big effect on the mean. And so in a symmetric distribution, so I'll draw a couple pictures here. So in a symmetric distribution, where your outliers are kind of balanced on both sides, then right here in the middle, your mean is going to be essentially more or less equal to your median. They're going to be basically the same. And the mean has a lot of really nice properties about it that are really easy to work with in math, because it's not like an algorithm with medians. Like medians, you have to sort it and then you have to find the middle. It's not really an arithmetic thing, but the mean is. And so all you do is just add numbers up and divide. But anyways, so we usually use the mean for symmetric distributions. But when you start to have skewed distributions, so for example, in a skewed right distribution, your median might be, say, like right here. But what do you think is going to happen to the mean? Knowing that it's not resistant. It's going to get pushed which way? Down or up? It's going to get pushed up. Okay? So then your mean is going to get pulled towards the skewness. Gets pulled toward the skew, which is the same as saying getting pulled towards the tail, which is the same as saying getting pulled towards the outliers. So that mean gets dragged towards the skew direction. And so it's not really actually necessarily going to be your best representative of the center if you know you have outliers. And the opposite thing happens in skewed left distributions, right? Your median may be somewhere like here, but then your mean is going to go where? Your mean is going to get pulled down. Okay, so in both of these situations, the mean gets pulled towards the skew, whichever direction that is. Okay, so then if you're thinking about doing a study about like salaries, for example, like income, and you have to decide which statistic is the best statistic to actually observe in populations. Well, which one's going to be better? Should you observe average salary or should you observe median salary? You should observe median salary, because median salary is, we know that incomes are skewed, and so median salary is a better measure of center. And if the median moves, that means a lot more than if the mean moves, right? Because like in this class, let's say we looked at all of our annual incomes, right? And we calculated the mean. And then let's say Bill Gates walks in the door and joins our class, and we redo it. Well, what's going to happen to our average income of now? It's like goes from 27 to 28 people. Our average income is going to skyrocket. Did any of us actually get richer? No, it doesn't mean anything, right? But if I measured our median income, and then Bill Gates walks in the room, the median is not going to respond to that. It's going to go a bump up maybe a little, but it's not going to respond to the magnitude. So then, if the median income goes up, that means something. That means everybody's moving up, right? That's what the median tells you. It means everybody's moving up, not just people on one end, if that makes sense. Okay? So then I'll just add that down here. Typically, I consider median is a more honest measure for skewed distributions. Okay. All right. Let's see. Where are we going next? Okay. What we got? I will do a little bit. All right. So measures. So those are the mean and the median. Those are the main measures of center. And the main difference between them is the mean is nice mathematically, but the median doesn't get affected by outliers. That's the moral of the story. Measures of dispersion. This is another way to say measures of spread. We also want to come up with some of those, and you've probably seen some. So, like for example, one thing we use for measures of dispersion is we use maybe the range. You know, like how far is it over from the bottom to the top? And then for one thing we're also going to look at is we're going to look at percentiles. Might be able to help us see the spread of a data set, and we'll talk more about what those are later. And then we're also going to use something called the standard deviation. Okay. And the standard deviation is something pretty unique to statistics, but it's really widely used. So it's a really important value to describe a data set, turns out. Okay, so as far as range goes, range is a pretty simple one. How do you calculate the range of a data set?
Highest numbers and lowest number.
Yeah, so in data sets, normally we call them max and mins, but yeah, it's just the highest and the lowest numbers. You just take the max value, subtract off the min value, boom, that gives you your range. So like for our pulse data, what would be our range here?
86 minus 60.
Yeah, our highest number is 86, our lowest number is 60, and so it looks like our range is 26 beats per minute, right? Okay. Now the thing about the range, and this is kind of what I was talking about yesterday, is the range doesn't tell us a lot of information because, like, you could have two distributions. Excuse me. They have the same range, but they have really different shapes and behavior, right? So, sorry. What's the main differences between those two distributions?
One's symmetrical, the other's not.
Yeah, you could have the same range, but you could have two data sets that don't even share the same shape. Like one could be symmetrical, one could be there. And then the other thing too is like, you know, some might be really piled up in one spot, and some might be more spread out. So that's why we wanted to come up with other numbers to describe dispersion, because range just isn't that informative. Okay, so that's where the standard deviation comes in. This is where it gets really fun. So here's what the standard deviation is attempting to do. Let's start with that. All right, it measures something, and what it measures is how far away, on average, observations are from the mean. Okay. So, what that means is, it means that, like, what should happen is like let's say you had a bell-shaped distribution that looked like that, right? And then let's say that you might have another bell-shaped distribution that's shaped like that, right? So shape's not everything, and really neither is center, because like these could be the same center, and they're the same shape, but what's the difference between these two distributions?
It's more spread out.
Yeah, here almost everyone's piled up right around the same place, right? Everybody's really kind of condensed right around one value. Here, people are very spread out, okay? And so the standard deviation is a number that we try to use to describe what we're dealing with. Like, am I dealing with a data set like this, or am I dealing with a data set like that? So, the way we measure it is, okay, so we use a little s, and little s always denotes sample standard deviation. It's easy to remember because it's sample standard deviation, lots of s's. So estimate the sample standard deviation. All right, so then we want to measure how far away things are. So like, let's say if this was the mean, right, and you're somewhere below average, then you can measure your distance away from it, right? You just do like where you are minus the mean, right? So part of the standard deviation is first we took each observation and you subtract the mean. So you take each x value and you subtract off the sample mean. But the problem with that is that some people are going to be above average and some people are going to be below average. And if you take a bunch of positive and negative numbers and if you add them all up, what do you think is going to happen? Like, if half the people are positive and half the people are negative and then you add them all up, what's going to happen? They're all going to cancel out. That's useless. Because we want to measure distance, so we want to turn these things positive. Well, how do you take negative numbers and turn them positive? Yeah, there's two options. You could use absolute value, but nobody likes absolute values for a lot of reasons. And so instead what we do is we square them. Okay, so we square, so in here, first we measure how far away are you with the sign. And then we square those values to get rid of the sign so everything's positive. And since we're averaging things out, right, average means add them all up and divide by sample size. But for standard deviation, we actually divide by one less than the sample size. And the reason for that is, well, there's a reason for it, but I'm hoping you'll just trust me that that's the rule. If you guys are okay with that.
So it's sample size minus 1.
Exactly. It's actually, you divide by one less than the sample size. Now, that number right there is actually called the variance, which is something we don't use so much in this class. We use the standard deviation, which is the square root of all that. So, okay. So this is the formula. This is the formula for calculating sample standard deviation. Now, it looks very complicated, and it kind of is. So the easiest way to do it is just to like look at an example so I can show you how it works. Okay, and then you can also do this in your calculator pretty quick, which I'll talk a little bit about first. But first I'll just kind of show you how it works. Okay, so, and there's applications we're going to get into as well. There's a lot of applications in standard deviation. So before I go there, I want to show you how to do this. This will be, we got just enough time to do this example, so that way at least you see it in action. So here's the way, so the formula is the square root, you know, of the sum of each observation minus the mean squared, all over one less than the sample size. I'm just copying it down there. Okay, this is why I let you bring a note sheet into tests, because we start to acquire like a lot of formulas, and so any formulas that you think you might need on an exam, you need to provide that yourself, because I don't put formulas on the exam. Okay, I let you guys use your sheet, and then you put your formulas down, and you can add whatever else you want to the note sheet as well. Okay, so the way this works, the best way to do this if you're going to do it by hand is you start by making a table, okay, and you just put all the xi's, those are just all your data points. So it's like, here's 76, 60, 60, 81, 72, and they don't have to be in order. The order doesn't matter with standard deviation. Okay? Now, if you look in here, order of operations, you're going to have to do the subtraction first. So then what you do is you need the mean. So you need, if you remember, we already did this, right? What was our x bar? Wasn't it?
74.2.
It was 74.2. Okay. So then we need to take each of these observations and we need to subtract the average. So like 76 minus 74.2, what's that, 1.8? 1.8, okay? And then you go, 60 minus 74.2, and then we'll do that for all of these, all the way down to here. Okay, so you need to subtract all those. So then this one would come up to be what, negative 14.2? Negative 14.2. Somebody correct me if I'm wrong on these. 81 minus 74.2, is that 6.8? Is that right? 6.8. 72 minus 74.2, that'd be negative 2.2. 80 minus 74.2, that'd be what, 5.8? So 5.8 there. 86 minus 74.2, what's that, 11.8? And then 73 minus 7.2, that's negative 1.2, right? Okay, so these are all called deviations. Because that's literally what they are. It's showing you how far each thing deviates from the average. So this person's 1.8 above average, this person's 14.2 below average, and so on. Okay, it's literally the deviation. Now, if you add all those up, though, a bunch of those are going to cancel out. You're going to get something really close to 0. So that's why in the formula, we take each of those deviations and square them. So now we're going to do 1.8 squared, and we're going to do negative 14.2 squared, and we're going to go all the way down. And you guys are going to have to help me because I can't square these numbers in my head. Okay, something like that. Okay, so you just got to go down the list. So like, that's going to turn everything positive. So this is how you're going to get all your positives. So my deviation here is 1.8. 1.8 squared is what? Somebody help. Let's pull out the calculators.
3.24.
3.24. What's 14.2 squared? 201.64. So that means this one will be 201.64. You guys should probably just, if a couple people don't mind checking some of these, just so we have a couple people looking at them, because it matters that they're right. But so what's 6.8 squared?
46.24.
46.24. How about 2.2 squared?
Negative 4.84.
But it will be turned positive because of the squaring. Yeah, 4.84. 5.8 squared? 33 point what? 64. So this one would be 33.64. Okay. And then here 11.8 squared would be what? 139.24. And then 1.2 squared was at 1.44. Okay. These are called your squared deviations. Because that's literally what they are. You took all those deviations and you squared them. Now, what does our formula tell you to do with all those squared deviations? Yeah. The sigma says sum them, add them. All right? So then you just go down and you just add them. Boom, plus that, 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 plus that. And at the bottom, let's see if a few people get the same answer. I don't know. I have no idea what the answer is. So. I feel like it's going to be like 600 or 700. I'm not sure.
Is what I got.
665.56? Sounds familiar.
665.56.
Cool. So these should add up to 665.56. This right here, this is the sum of the squared deviations in your formula. Okay? And so now that's the hard part, basically. So getting that sum is the hard part, but what it involves is first you get the deviations, then you square them to make them positive and adding them up. But from that point, there's not that much left to do in the formula because we already now have that numerator, which is 665.56. Then down here, well, what was our sample size?
9.
It was 9. So we're not going to divide by 9 in the denominator. We're going to do 665.56 and divide it by 8 before we take the square root. Okay. Now, what is 665.56 divided by 8?
83.195.
83.195. Is there anything else there? Or is that it?
That was it. That's probably
Perfect. And then you're going to take the square root of that and we'll just approximate it.
9.12.
If you round to 2 decimal places, there you go. Okay. Okay. And yeah, go ahead.
Is there a reason that, like, when we learned this in psychology, we didn't subtract the one? Or we
Yes. You
Is
didn't
it our,
subtract the 1.
Is it not standard deviation if we didn't subtract the 1?
Yes. Hold the thought because I'm going to talk about it in just a
Okay.
second. There's a reason. Yes, there is a reason that you may not divide by 1. Or,
Subtract, right?
right.
Okay.
Other questions about the example, though, but then I'll answer that question before. Yeah.
So this is like, if it's just when they ask for standard deviations, so all you
Yes, this is literally how the standard deviation is calculated. It's one number. And you could use it, so there's a couple ways we're going to use the standard deviation. Okay, it means something, I promise. It's not just like a stupid number that you get calculated and forget about. But you can also use it to compare, because if another population came behind and they had a bigger standard deviation or a smaller standard deviation, that's telling you whether that population is more condensed or more spread out than this one. And then we have other ways to use it. Okay. Now, what you were asking about with the n and the n minus 1, can I move from this slide right now, or does anybody need to go over anything else on it?
Can I take a picture of it?
Yeah, sure. I do upload these also, and then they're on my videos as well. But yes, please take a picture. That's fine. The reason you may or may not do n minus 1, it has to do with population versus sample. That's the answer. If you're dealing with sample data, so in the sample standard deviation, okay, that's what we call little s. That is sample data. You're dealing with sample means and sample sizes, and you subtract the 1. And the reason for that is complicated, but the moral of the story is when you take a sample, if you don't divide by n minus 1, your standard deviation will actually be what we call a bias estimator. And so the n minus 1 is a correction to make it unbiased. That's the simple answer. It's complicated. It's not easy. It's like in your first graduate statistics course, you have to prove that that's an unbiased estimate. It's pretty complicated. It's not easy. But if you have population data, so if you didn't take a sample, like you actually have your entire population, the population standard deviation we denote with another Greek letter, which is a sigma. It's a lowercase sigma, not an uppercase sigma. And it is the sum of the observations, but then you would have the true mean, and you would only divide by the population size. So it's the same formula, but you don't do the minus 1 correction at the bottom because you have population data, and so you don't have the sampling bias. So this is a correction for sampling bias. But if you have population data, you don't need it. And that's why you may have seen it without an n minus 1 before. Okay. So this little thing, this is a sigma. Not to be confused with that sigma, because one's lowercase and one's uppercase. And remember, the idea is we use x bar to estimate mu, and similarly, we use s to estimate sigma. So thinking in terms of the big picture of statistics, you always have the difference between population parameters versus sample statistics. So up here, everything's sample standard deviation, sample mean, sample size. This is population standard deviation, population mean, population size, which is usually denoted with a big N. But we don't spend a lot of time, we don't really spend that much time dealing with population stuff, because the whole goal of this class is talk about inferential statistics, which are when all you have is a sample, and you're trying to use it to make predictions or test hypotheses about your population.
So will we use the population much?
No, this we really will almost never
Okay.
ever use this. Yeah, we're working with a different type of.
Okay.
This class is focused on when you don't have population data. You're only dealing with sample data. So we focus mostly on sample data and sample formulas. Yeah. Okay. We're out of time.
Yeah, I'm gonna argue with them later.
actually in another pocket that I want to
Yeah, what's up?
I have a question. So 74.2, that's the mean that was before you added the outlier?
Yeah.
So when you do standard deviation, you don't add the outlier?
Well, it was just in this case, I did it without the outlier. So the outlier I just threw in there to look at what happens to means and medians. But when I came back to this example, I was just defaulting to the original data set.
Okay, so it will like in the question it'll say include the outlier or not? Or?
Yeah, or I'll give you the numbers that I want you to use.
Oh, okay.
Yeah.
And just one more question. I'm sorry. Well, because I don't know if you say we don't have to use this a lot. Population. This is the parameter.
Mm-hmm.
So like that's the percentage or?
No, this would be the population mean. It's the true mean. Like there is some true number of hours of sleep that everybody got last night, but we'll never really know it because we'll only have a sample mean. So we could ask 100 people and they could give us an answer and we could average it, but
Right.
that's not the population mean. It's just the sample mean. So normally this is unknown.
Okay.
Mu is usually, we don't know what that number is.
So we're not really gonna use this one, you said.
Right, we're not gonna, well, we will some, but we're focused mostly on sample stuff
Okay. Thank you
in
so
this
much.
class, yeah.
When we